we are going to look at what happens if we're given a voltage, a function for voltage, and can we find the electric field from that function. Okay, so it's going to be kind of a simple example. Found my pen here. No, I have my pen somewhere. Okay. But still helpful, I hope. Okay, so let's say we're given a function for a voltage. So let me draw an axis here. Okay, so this is x, and this is v. Okay, and the function for this voltage looks something like this. Pretty much a quadratic here. We're told that the voltage is given to us as a, as voltage is a function of x. I think I do need to clean my screen here. I think that's why I'm getting such poor contact here. Voltage equals 50 volts per meter squared times x squared. Okay, so that is our function for voltage. 50 volts per meter squared times x squared gives us our voltage, and what we want to do is find E. Find E, electric field. At x x equals 2.0 meters. Okay, so given this function, we want to find the electric field at 2.0 meters. Okay, so it's not too hard, and let me write out the equation. How do we get electric field from voltage? Well, the equation that we saw earlier is this. Okay, where that, again, this is like an upside down triangle. It's called the del operator. In our case, since we're talking about the x component, it will be negative dv over dx I hat. Okay, so we're just going to need to take the derivative of voltage, and the negative derivative of voltage, and that gives me my electric field in the x direction. Okay, now what that means graphically is that we're just looking at the slope, right? So the negative slope. So you can see here, voltage is has a positive slope, right? No matter where, like, let's say we're looking at this point. Say we're looking at this point right here. Well, at that point, the red dot, we have a positive slope. That means our electric field is going to be going in the negative direction, right? So I'm just applying this equation here to our slope. If you get a positive slope, that's what dv over dx tells you, right? Slope. If it gives a positive slope, then your electric field will be going in the negative direction, right? In the negative x direction. Okay, and you can kind of see what happens to this to this electric field. As you go up along this voltage, your slope is getting greater and greater and greater. So your electric field is going to be going greater, getting stronger and stronger and stronger. Right. So it's one of the things we've talked about, that as voltage changes, the quicker voltage changes, the stronger your electric field becomes. So in this equation here, my electric field is increasing as we go in the x direction, because that slope is increasing. Okay, so that's what this equation tells me here. Now mathematically, pretty easy. All we gotta do is take the derivative of this function. So let's do that now. Oops. So electric field equals negative d over dx of my function. I'm just going to drop off the units here. 50 x squared, and it's going to be I hat. Okay, and of course this is my vector. Technically, I'm only finding the x component of electric field because I don't know how this voltage is changing in the y or in the x. But look, for the sake of this problem, I'm going to assume that there is no x or y, there's no y or z directions, just x. Something like that would be like a parallel plate capacitor. Parallel plate capacitors will give us that kind of behavior. Okay, so let's take the negative derivative. So we get negative, well, that's pretty easy. So negative 100 x I hat. And we just plug in. So here, I mean, that's my function. So at, I don't know why it's like it must be because it's dirty. At x equals 2, you just plug in. Electric field equals negative 100 times 2. That gives us 200, negative 200. And then my units, of course, newtons. Oh man. Units per kilo. Okay. So pretty easy, I think, when you go from electric field to, or from voltage to electric field, or from potential to electric field. All we're doing is the negative derivative. All right, and that's how we do that. Of course, once you get electric field, you can find forces. Like if you put, what would be, like if the question asked, what would be the force of a charge if you put it at x equals 2.0, you would have to do all this anyway to find electric field. And then if that was a question, you go ahead and do F equals QE, right, to find that force. So sometimes, you know, you'll still have to go back to those equations if it's asking for it, if it's asking for force, but that's how you would do that. Okay, so let's talk about the potential in conductors. Okay, so I'm gonna go back here. With conductors. So if we're talking about equilibrium, so in equilibrium, in static equilibrium, actually, pretty sure that applies to non-static equilibrium as well. Well, we can always go back. All right. So in static equilibrium, conductors maintain the same voltage throughout. Okay. So I have this example here on my PowerPoint, which I'll share with you guys. Okay, so here's this example. I have two metal spheres connected by a wire. All right. As soon as you connect those two spheres, even if one is charged and the other one is not, the charge will disperse, you know, among itself. So it goes to equilibrium. That does not mean they will have the same charge on each sphere, right? One sphere has a more surface area than the other. So the sphere with larger surface area, we could say it this way, could accommodate more charge. Okay, so they're not going to have the same charge, and they're definitely not going to have the same electric field, right? If one sphere has more charge than the other, then, well, in this case, a larger sphere has more charge than the other, then that larger sphere is also going to have a larger electric field. But what is going to be true, because they're both conductors, is that the voltage on both of them will be the same. Okay, so that's very characteristic of a conductor. You have these conductors, and these conductors will maintain the same voltage throughout. Okay, important characteristic there. Okay, here's a kind of another example of that. All right, so you have these this battery, and I think we talked about a battery. I'll come back to that. What the battery does, all it does is that it keeps the voltage the same. It keeps the same difference in voltage. So you have a battery here. That battery, let me write on this here. Okay, that battery right here keeps will have a voltage of 0. And up here, what the battery will do is maintain a voltage of 3 volts. Okay, so the positive end of the battery is 3 volts. The negative end of the battery is 0 volts. It doesn't have to be those specific numbers as long as the difference is 3. So I could have said, just to show you how that the numbers don't really matter, it's the difference that matters. So I could have set this to positive 1.5. And this would be a negative 1.5. Either way, right? Either way, you have that difference of 3 volts, whichever way you're looking at it. So let me just stick with the blue here. So I'll erase the red. Okay, so 3 volts on top, 0 volts on the bottom. So what I've been saying is that the potential stays the same for the whole conductor. So this is 3 volts for the top part of the battery. Whoops, where'd it go? This 3 volts here will keep this whole wire set to 3 volts. Same thing down here. If the battery keeps this as 0 volts, then it sets the whole wire to 0 volts there. Okay, so we could kind of answer the question, what is the potential difference between points 1 and 2? Well, if this whole wire is 3 volts and this whole wire on the bottom is 0 volts, then we know the difference, right? Which would be 3. Okay, so really kind of important point with conductors. We'll use this in the next chapter when we start talking about circuits, that the voltage stays the same within a wire in a circuit. We'll talk about it with capacitors, definitely. Okay, so it definitely keeps the same voltage. Okay, now I'm gonna go back to my whiteboard here. Okay, so when we're talking about static equilibrium, definitely is maintained in non-static equilibrium. So and I'm going a little bit ahead of myself, but I'm just kind of setting up for our next chapter. So when you have currents, so say non-static charges or moving charges. Okay, potential may change, but even then, pretty slightly. Slight difference, slight changes in a wire. Okay, so we'll talk about that later on because I'm starting to get into some circuit theory here, but it's definitely true in electro and static equilibrium that voltage is going to be the same. Even when you have current running through it, voltage will still pretty much be the same within a wire. Okay, so I don't want to make like a huge distinction between static equilibrium, because when we don't have static equilibrium, for the most part, we still treat it to be the same same potential in a wire. Okay, so in conductors, voltage stays the same. What is creating this voltage? Okay, so let me put this in a different color here. Okay, so it is batteries. So batteries, the whole point of a battery, create and maintain this voltage. Okay, so that's the whole point of a battery. So if I have a battery here, let me sketch a battery really quick on my screen here. Here's a battery, just to say 1.5 volts. Like I said in the previous example, the positive end of the battery is going to be held at 1.5, and the bottom, the negative part of the battery, is also held 1.5. If I put another battery connected to it, another 1.5 watt battery, and I have a wire, kind of like I did before. This wire down here at the bottom part, this wire, this here, this point here, this point here, and this point here, voltage will be 0. And at the top, this point here, anywhere along this wire really, the voltage would be what? What would the voltage be at the top there? Voltage is 0 at the bottom, got two 1.5 volt batteries. The voltage at any point on that wire at the top would be what number? Go up this way. Those batteries are increasing your voltage. How much is it increasing? Yeah, 3. Okay, so as you go up here, your voltage increases by 1.5, right? It goes from the negative end to the positive end of the battery. I didn't think I do. I mean, you guys don't know. I think sure you do know. Which side's the negative, which side's the positive, right? I'm sure all of you have plugged in batteries before. So 1.5 volt battery there. Then you go to the next one. Oh, no, I didn't mean to erase it. Okay. Then you go to the next one, next battery. That's another 1.5 volt increase. So these two 1.5 volt battery gives you a total increase of 3. So by the time you get to the top wire, that voltage has been raised up to a voltage of 3. Okay, so that's what the battery does. The battery maintains that difference in voltage. I should have put that wording that's a little bit more precise. Maintains that difference in voltage. Okay, that's what batteries do. Okay, so what we're going to do with this, I'm going to put a plate on the end of these wires. Okay, so let me put a plate like this in here. Okay, so I'll connect these wires to a plate. And so what the battery is going to do, in order to maintain that voltage, it's going to pump out charges. So it's going to take out negative charges from the top plate, pull them out this way, and so these are my negative charges, and then put them in this plate here. So here you start to accumulate negative charges because I took it out from the top plate. If I'm missing positive negative charges on the top, what's left on the top then? You should get a whole bunch of positives. Okay. So this is essentially a capacitor. Okay, you start connecting these batteries to these large sheets, and then now you start having what we call capacitance. Okay, so let me more formally define this. Let's go back to my PowerPoint here. Okay. So connect to the battery, and they start accumulating charge. Okay, so a capacitor, once you connect it to a battery, it's going to start storing up charge on those capacitors. How much charge it holds kind of depends on what we call capacitance. Okay, so eventually the voltage difference between those two plates is going to be the same voltage difference between the battery, right? And so that's what I've been kind of stressing to build up to this point, that if all these are conductors, right? The wire is a conductor, the plate is a conductor. If all of it is a conductor, then those conductors maintain their voltage. So you have the same voltage in this plate and the wires. All these have the same voltage here. And same thing down here. This positive plate and this wire will maintain whatever positive voltage it has. So I go back to my example of this is the 3.0 volt battery here. This plate will be at 3.0 volts. This negative plate will be at 0 volts. Same voltage same voltage difference of your battery. Okay, so you start to have this voltage, and we're going to quantify, how much charge can this capacitor hold at a particular voltage? Well, we call that capacitance. So how much charge they hold depends on this thing we're calling capacitance, and capacitance is defined by how much charge is held by the capacitor at a specific voltage, at a certain voltage. Okay, so how much charge is held per volts. So this is our equation for capacitance right here. Capacitance is Q over V, where Q is the charge on each plate. It is not the total charge on both plates, right? The total charge on both plates. If you add the charge on the positive plate plus the charge of the negative plate, you would always get 0. Okay, so I'm just talking about the magnitude of charge on each plate. All right, so that's Q. V is what voltage is that capacitor set to. Okay, and then we have units for capacitance. So our units for capacitance is a farad. Okay, so as you guys write this down and are looking it over, one thing about capacitance that I kind of run into as I'm teaching, I'm go put up my video here for my quick discussion. So one thing I run into a lot is that this confusion about capacitance meaning how much charge it could possibly hold. Okay, a capacitor, if we're ignoring something called dielectric breakdown, assuming super ideal conditions, the capacitor could keep increasing the number of charge as long as that voltage increases. Okay, so don't think about capacitance as like, we think about what's the capacitance of a restaurant, right? How many people can it hold? That's not the same idea here. All right, the idea here is a ratio, right? You can see that in the PowerPoints there. It's a ratio of charge to voltage. That's what that capacitance is. So there is a certain ratio of how much charge a capacitor could hold, at a certain voltage. If you want more charge, you're just going to increase the voltage, and you get more charge in your capacitor. But it is limited by this ratio. Okay, I hope that kind of makes sense. Okay, so capacitance is not the total amount of charge a capacitor could hold. That's not correct. What capacitance is, you can think of it as how much charge a capacitor could hold per voltage. Okay, so with more voltage, you could have more charge. All right, if I'm talking about that restaurant scenario or example or illustration that I mentioned, capacitance is not how much people could go in a restaurant. It's how much people could go at a restaurant per square foot, right? So if you increase the square footage of a restaurant, you can have more people. Okay, that's what capacitance is, right? How much charge you have per voltage. Okay, I hope that was helpful and not confusing. Okay, that's my little spiel on capacitance. Okay, so let me go back to my whiteboard. Okay, so we're talking about capacitance, and we already have one equation. I'm going to draw my capacitor again. Okay, here's my capacitor. We'll say the top is just full of positive charge. And the bottom we'll say is negative charge. I can't remember if I'm doing the same colors as last time, but because colors aren't super important. Okay, and we said that the capacitance is defined as Q over V, right? So capacitance C equals Q over V. All right, charge over voltage. And again, I mean, I could be even more specific with that voltage because I'm really talking about the difference in voltage. So, all right, this difference in voltage here. All right, so I'm gonna make a substitution here. Instead of Q over delta V, remember we're parallel plate capacitor, we have constant electric fields, right? So voltage, we could use this equation that we saw in earlier electric field. I'm just going to focus on the magnitude of electric field here. Equals your change in voltage over change of distance. Okay, change in voltage over change of distance. Now, where did I get that equation from? Go back a few a few slides here. Where is it? Where somewhere in the beginning? Right here. I got it from here. Now, how come I went from dV over dr to delta V over delta x? Well, what can you tell me about the electric field in a parallel plate capacitor? In a parallel plate capacitor, electric fields are constant, right? This is constant. So what that's telling me is that you have a constant rate of change of your voltage over distance. Okay, so that's why, going back to this, I just put delta V over delta x, right? That rate of change, this ratio is being held constant because our electric field is constant. Okay, so in our case here for this parallel plate capacitor, the distance I'm talking about, do this in blue, I guess, is this distance right here. I'll call that distance D. Okay, so I get voltage or change in voltage equals E, oops, E times D. Okay, so I'm just solving for delta V there. Then I get, let me plug it in for my C now, Q over delta V, and now my delta V is E times D. Okay, let's go a little bit further with this. We know electric field in a parallel plate, in a capacitor. You guys remember is eta over epsilon 0. That's my electric field, or I could put it in terms of, remember eta is charge density, right? Surface charge density. So eta, I'm gonna plug in Q over A. Q over A. So Q over epsilon 0 times area, I'm gonna take that and plug it into E. Take that, plug it in there. All right, so simplifying, we get C equals, what am I missing here? Epsilon 0 A over D. Okay, so we got two equations for capacitance here. Equation 1 is kind of the definition of capacitance, Q over delta V. Equation 2 looks at capacitance in terms of the actual physical construction. we could find the capacitance if we know the area of the plates and we know the distance between the plates. Okay, so that allows us to find capacitance just from knowing the physical dimensions of the actual capacitors themselves. All right, so that's our introduction to capacitors, and now we're gonna do a couple of just calculations, and then we're gonna look at capacitors in series and in parallel. So we're gonna start looking at circuits this chapter as we wrap up this chapter today. All right, so let's just do one example just to get used to these equations. Not a very difficult example, but just something to get used to it. So it shouldn't, this example is not going to be difficult, and so we should go through it pretty quickly. All right, so let me read the question. We have a capacitor, the spacing between two plates of a 1.0 microfarad parallel plate capacitor is 0.070 millimeters. Okay, so that's a distance between the plate. And asking two questions: what is the surface area of the plates, and how much charge is on the batteries if this capacitor is attached to a 1.5 volt battery? All right, so A. All right, so surface area of plates. Well, we know capacitance is related to surface area from this equation here. Okay. We have C, right? This is our capacitance right here. And we have distance. That was that value there. So pretty easy as far as, just again, all I want to do is get used to these equations. So that's all we're doing with this example. I could rearrange the equation, solve for A, right? Surface area. So A equals C times D over epsilon 0. Okay, and of course we could plug in there. So plug in for C, 1.0 microfarads, so times 10 to the negative 6. Distance, watch out for your distance, right? You got this all has to be SI units. So 7.0 times 10 to the negative, that'll be negative 5 meters, all over epsilon 0, 8.85. Times 10 to the negative 12. Okay, and we get our area, which I'm not sure what it is. I think I actually have it in the next slide. There it is. That was easy. 7.9. Oh, that's huge. 7.9 meters squared for our area, which is, I mean, if you think about that as an area for a capacitor, we're looking at a pretty large capacitor here. Okay. Part B, how much charge on the plates of this capacitor is attached to a 1.5 volt battery? Well, we could do that pretty easily too. So we have our other equation for C, which relates charge. Oh man, I don't know why I did that. Relates charge to voltage. So we got Q, we're looking for charge, equals C times V. We'll be using that quite a bit as we continue looking at capacitors. And we have those numbers, right? 1.0 microfarads. And the voltage is 1.5. So multiply those together, 1.5 times 1, pretty easy, 1.5 microcoulombs. Okay. All right, so again, pretty easy example just to get used to using our capacitance. what we're going to do next is take that capacitor, or take several capacitors now, and start linking them together. And so we're going to start get into circuits here. As we started to get into circuits, we're going to look at different kinds of construction of circuits, like parallel setups and series setups. And so this is a really, this last part of the chapter is really an introduction to circuits, right? We don't have to talk about current just yet. We're going to hold that off until the next chapter, but we're going to start getting into circuits here.